Okay, so what's happening today? Today we're going to start chapter 2 on series. So we're going to start with an introduction. And this introduction is going to include looking at two interesting series. I'll tell you what a series is in a moment, if you haven't read about it already. So investigate two nice important examples. Now for that, we probably won't open up many new, good observation of rule 2 there, very good, thank you. We probably won't open up many new exercises, although there are a few preliminary exercises on series in page 18. Questions 1 and 2 are kind of investigatory ones. But you do, in the tutorials this week, for my half, you could be working on finishing off the questions on sequences. And remember, you do have this guidance sheet that I gave you, which was kind of leading you by the hand through the construction of the proof for the quotient form of the algebra of limits result for sequences. So I'd like you to keep working on that, and the tutorials this week will give you an opportunity to discuss that with your tutor. Okay, I'll get them to go through it with you and answer any questions you might have. Okay? So, and I put a picture up there of, everybody knows what that is? The Beetham Tower at the bottom of Deansgate in Manchester. It's kind of iconic building for Manchester these days. And that, what we're going to discuss today has some kind of connection with that. Okay, interesting tower with an overhang there halfway up it. So that's going to connect with some of the things we're going to talk about today. Okay. So we look at chapter 2, and so it's about series. So we have to tell you what a series is. We already know about sequences, and we've been looking at infinite sequences, and we've been studying the idea of convergence. Okay? How a sequence can, as you go far out the sequence, how the sequence elements can be getting closer and closer to some limiting value. Now, a series is the next kind of object to look at, and a series is very simply what you get when you take a sequence and you add together all the elements in the sequence. Or, now that's already a bit of a problem because sequences are, the sequences we've been looking at are infinite sequences. So how do you add together an infinite number of things? So you might like to phrase it like that. You can also phrase it as looking at the process of adding up, all the terms in a sequence. So take the first one, you add on the second one. Then you add on the third element from the sequence, add on the fourth element from the sequence. Okay? So it's a process of adding up terms. Of course, if the sequence is infinite, if the sequence is unending, then that process is going to be unending as well. Okay? So that's, in a nutshell, what a series is. And this first page just introduces some notation. So you can write out all the terms in a series, 1 minus 2 plus 3 minus 4 plus 5, etc. Okay, so the terms are 1 minus 2 plus 3 minus 4. Of course, that'll become extremely laborious writing out long sums all the time. So we have a compact notation for writing sums, and that's the sigma notation. So this letter here is the capital Greek letter sigma, pronounced as an S. The equivalent of our S, letter S. That's the capital version. So that's used to denote series or summations, sums, adding things. Okay? And it's a nice symbol to use. It's got a nice long, flat, horizontal bars at the top and bottom, which give us nice space to put in superscripts at the top and subscripts at the bottom. So this symbol here, which you read, this symbol here in the middle, which you read as sigma, or the sum from k equals 1 to 10 of this term here. Minus 1 to the power k minus 1 times k. That is exactly that sum at the top, 1 minus 2 plus 3 minus 4 plus 5, etc. So the first thing to do is satisfy yourself that those two things mean the same. So this summation index here, you see the -1 to the power k minus 1. Well, when you take -1 to any integer power, you either get +1 or -1. Yeah, depending on whether the power is an odd or an even number. So when you have, you see the starting off value of the index is k equals 1. When k equals 1, we have -1 to the power 0. And by definition, anything to the power 0, or anything non-zero to the power 0 is by definition 1. When k is equal, so you get a +1 positive sign multiplying k equals 1 for the first term. When k equals 2, you've got -1 to the power 2 minus 1. So you've got -1 to the power 1, which gives you -1. So -1 multiplies k equals 2. So that's why there's a -2 in the sum. Okay? And so on. That -1 to the power k minus 1, that produces an alternating positive and negative sign. So we're simply adding up that alternating positive and negative sign multiplied by k. And k is starting at 1 and going to 10. So more generally, on the next line there, you could have sigma, the sum from n equals 1 to capital N of the terms xn. So that denotes the sum x1 plus x2 plus x3 plus x4, etc., and ending with the term x capital N. Okay? Because capital N is the top superscript in the summation sum, okay? And the sigma. Is everybody okay on that notation, that sigma notation? I mean, you've probably come across it before. That's what it is. There's a very similar notation for products, which uses the capital version of the letter pi. It just looks like a large letter pi. Again, there's a nice bar at the top for superscript limits and underneath it for starting values. So very similar notation, pi used to denote products. So pi is the Greek letter, which is equivalent to our p. So it's used for products, multiplying things together. Okay, but here we're looking at sigma for sums or summation or series. And of course, well, okay, finite sums, well, they might be long and they might be complicated, but conceptually they don't pose a problem. A finite sum of numbers, you just add all the numbers up and it comes to some value. There's no great theoretical difficulty with the concept of a finite sum. What's a little bit more tricky to get a hold of is an infinite sum or an infinite series. So this would be denoted in general by a sigma notation here, the third sigma notation, the sum from n equals 1 to infinity of x. And that is denoting the process x1 plus x2 plus x3 plus x4, x5, x6. And it goes on without end, adding up all the terms in an infinite sequence. Okay? Now that immediately presents a conceptual problem. I mean, does that even make sense? A finite sum, there's no problem. Okay, even if it's really long, it might take a number of lifetimes to add it up, to carry it out, but there's no logical difficulty with the notion of a finite sum. When you start talking about an infinite process of adding things together, straight away that seems a bit dodgy almost. Does it even make sense? Is there any, is it valid to talk about such things? Well, we can do that in mathematics, okay? And we do it using the ideas of convergence for sequences that we've already introduced, okay? So some of the times we're actually going to say that an infinite series, an infinite sum, can actually have a finite value. So we're going to encounter cases, and a large part of this chapter is getting tools that allow you to say sometimes that a certain infinite series has a finite sum. So you add together an infinite number of things, and you end up with just a number as the answer. So that seems a bit strange if you've never encountered it before. Now, we develop what that means with the use of some more terminology, and this is the partial sum. So we'll suppose we're talking about an infinite series, adding up from n equals 1 to infinity, adding up the elements xn. We can talk about the partial sums of that infinite series. The partial sums are finite objects, finite sums, adding up a finite collection of objects. So we have the partial sum sk, so the partial sum is an index itself, the kth partial sum. And that's what you get when you add up the first k elements from the series. Okay, you can see it there in the sigma notation. Sk is equal to the sum from n equals 1, the starting value, to n equals k, the ending value, of the elements xn. So that means x1 plus x2 plus x3 all the way up to xk. That's a partial sum. And now we can say, we can be very precise and say what it's going to mean for an infinite series, an infinite sum, to have a finite value. Okay? We say that an infinite series is convergent, because we've already talked about convergence for sequences. Well, we're going to say that an infinite series is convergent if the partial sums form a convergent sequence. So you've got a sequence of partial sums we're referring to here. S1, which is just the first element of x1. S2, which is x1 plus x2. S3, which is, maybe I'll write this down just to emphasize it. So here's our infinite series, and the sequence of partial sums looks like this. S1 is just x1, S2 is x1 plus x2, S3 is x1 plus x2 plus x3. I'll only write one more down. x1 all the way to x4. You get the picture. Now all these S things, there's no conceptual difficulty. They all have a particular value that you get from just adding those finite collection numbers. So there's no problem with the S numbers. That's a sequence of numbers. Okay, so we have a sequence, have an infinite sequence called the sequence of partial sums of the series. Okay, so it's an infinite sequence. And we know what it means for an infinite sequence to converge. So if it is the case that Sk is a convergent sequence, keep writing in what I'm saying. If Sk converges to L as k tends to infinity, then we say that the infinite series, it makes sense, it seems right, it makes sense to say this. We'll say that the infinite series is convergent, and we'll say that the value of the sum, and we'll write the sum from n equals 1 to infinity of xn, we'll actually write it's equal to L. So there will be situations, and we'll see some shortly, where we can say that an infinite series, adding up an infinite number of terms, that it does come to a finite number. And we'll see some examples now. Any questions about the notation or that definition of convergence? It'll become clearer when we look at some definitions. Look at some examples, excuse me. So the main thing to get is this definition of a partial sum for an infinite sequence. It's the sum from n equals 1 up to k of the elements xn. Okay, so you've got one S, one partial sum for every value of k. If this isn't the case, if the sequence of partial sums do not converge, then we say the series is divergent. And that can happen for that can happen in a few different ways. The first example we're going to look at is a divergence series, so one which does not have a convergent sequence of partial sums. Okay? So I'll switch back to the computer now in a second. Let's give you a chance to get that down. So the first, if the first thing I have to convince you of, or the first thing I have to demonstrate to you, is that convergent infinite series exist at all. Okay? Because it still seems a little bit strange that you can add up an infinite number of things and come to a finite answer. It's almost paradoxical. Of course, when we see some examples, the paradox will disappear. Okay. So our first example, example 2.1, is, should feel like a very familiar series, just adding up. Okay, adding up all the elements n from n equals 1, n equals 2, n equals 3, and so on without n. So that's that example in 2.1. So it's the series that begins 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now, agree with me now, please. That's a divergent series. What's happening to the partial sums? Well, S1 is equal to 1. S2 is 3. S3 is 6. S4 is 10, isn't it? What's happening to them? They're getting bigger. The partial sums are getting bigger. Is there any limit to how big they can get? No, because we're adding on larger and larger numbers each time, adding on larger and larger things each time. So it's just going to grow and grow and grow, and there's going to be no limit to how big it grows. If you want to see, if you want to see it grow to any particular size, you just have to wait around long enough, and eventually it will grow past that. Okay? It's an unbounded, and therefore divergent series. Okay? The sequence of partial sums is an unbounded, increasing sequence, so it's definitely not convergent. Next example, and obviously you could invent loads of divergent series now. Just construct an infinite sequence of large things and add them all together. If you add together an infinite collection of large things, it's going to get large and large, it'll be divergent. So you already appreciate now that if a series is to have any chance of converging, the things you're adding up have to be getting smaller. Because otherwise it's just going to grow without end. Okay, so they at least have to be getting smaller. So here's a nice infinite series, adding up the powers of a half. So you're adding up 1/2 plus the square of a half, plus the cube of a half, plus the 4th power of a half, plus the 5th power of a half. Can you ask yourself what that is equal to? But it's easy to, without too much difficulty, we can track the values of the partial sums of that series. So here we're looking at the series from n equals 1 to infinity of 1/2 to the power of n. So S1 is a half, isn't it? So there's S1. S2 is a half plus a quarter, which is 3/4, which is here. S3 is what? A half plus a quarter plus an 1/8, which is what? I know it's 9 o'clock, but 7/8. Anybody see the pattern? Of course, you all see the pattern. S4 is going to be 15/16. Sorry, am I doing this right? What's a half? This is a half plus a quarter. This is a half plus a quarter plus an eighth, which is 4 plus 2 plus 1. Yeah, 7 eighths. 15 sixteenths and so on. See, each time, it's like going on a walk from 0 to 1. You start off by taking a step of length a half, then you still got a distance half to go. But then you take a step of a quarter, which is half of the remaining distance. Then you take a step of an eighth. See, there's a quarter remaining, but you step forward an eighth, which is half of that. So you keep only advancing a half the distance towards the limit 1. So you're getting closer and closer to the limit 1, ever smaller steps. So you're never actually reaching 1 in any finite amount of time, but you're getting arbitrarily close to it. You're converging to 1. Clearly, Sk is convergent to 1 as k goes to infinity. So it's a convergent sequence of partial sums. Sequence of partial sums converging to a limit as the index k goes to infinity. It's a convergent sequence of partial sums. So we say the infinite series is convergent, and this has the value 1. So that's our first example of a convergent series. So it's all the terms in it are positive. You're adding up a load of positive things, but they're getting smaller and smaller. So although you're adding an infinite number of things, or advancing an infinite number of steps, but the step size is getting smaller each time. And the effect of that is that you never get past the point 1. You get arbitrarily close to it. If somebody specifies any degree of closeness to 1, you wait around long enough, and this walk will eventually get that close to 1, but it'll never get beyond 1. So it's converging to 1. Now the next example we're going to look at is called the harmonic series. So this is this series here, adding up 1 over m as m goes from 1 to infinity. So this is 1 plus 1/2 plus 1/3 plus 1/4 and so on. Now this kind of looks like the series we just looked at. Because it is an infinite number of positive steps. So you're taking a step of length 1, and a step of length 2, a step of length 3. And the step size is getting smaller. Step size is a half, a third, a quarter, a fifth, a sixth, and so on. The step size is getting smaller. However, it turns out that they're not getting small fast enough. You are still advancing forwards at a fast enough rate per step that you can actually travel any distance whatsoever. So this series is not convergent. Now here's a proof of that. I don't think the proof is in the notes. No, it just refers to it. So this is a proof that the harmonic series is not convergent. So it's 1 plus 1/2. We leave those terms alone. But then what we do is we start bracketing together the terms of the series. So I leave the first 2 terms alone. Then I bracket together the next 2 terms. Then I bracket together the next 4 terms. Then I'm going to bracket together the next 8 terms. Then I'm going to bracket together the next 16 terms, and so on. Okay, so we're grouping together, not changing the order of the terms in any way, but I'm just grouping them together in a certain way. So grouping together terms, doubling the size of each group as we go. So the first group is 2, the next group is 4, the next group is 8, the next group is 32, the next group is 64, and 128, and so on. And then what we do is I'll leave the first two terms as they are, but instead of a third, I'll write down a quarter. And instead of 1/5, 1/6, and 1/7, I'll write down 1/8. So that's, I've replaced a 5th, a 6th, a 7th, and then I've got the final 1/8 here. Then in the next group, see, I replaced all the elements in the group with what was at the end of the group. So the next group, I replace 17th with a 32nd, and so on. Replace all the elements with 32nds. What are we doing there? We're replacing fractions by fractions that are smaller. So instead of a third, I wrote down a quarter. Instead of a 5th, 6th, 7th, I wrote down an 8th each time. So we're replacing the terms from our original series with terms that are smaller. So our original series is greater than this. Yeah. However, we can see what this is. What's a quarter plus a quarter? Yeah. What's an 8 plus an 8 plus an 8 plus an 8? A half. You've got 8/16ths there, which is a half. You've got 16/32, which again is a half, and so on. So by grouping together terms in the harmonic series, what we observe is that, okay, so you see 1.5, then you wait around a bit and you see another half being generated. Then you wait around another bit longer for a few more terms to be added on, and again you see another half being generated to the series. You wait around twice as long, but eventually you see another half being generated. Now, you're having to wait around a long time, but you wait around twice as long again, and you'll see another half. Now, what do you get when you add 1 plus a half plus a half plus a half plus a half plus a half? What value does that equal? It's infinite. It doesn't have a value. It just gets larger and larger and larger. So this is a clearly divergent series. So we've got a divergent series at the bottom, an increasing unbounded series. However big you want it to be, you wait around long enough, eventually you will see the series grow past that limit. But the harmonic series at the top, how does it relate to this series? It's bigger than it, larger. It's a little bit hand-wavy, this proof, because there seems to be something funny going on, that you have to wait around longer and longer to see these halves being generated. But the essential idea, or the underlying idea, is correct. The harmonic series, it grows faster than a certain series which keeps generating halves. And so therefore, it is going to be an increasing unbounded series as well. Okay? So this shows that the harmonic series, sum of 1 over n, is divergent also. But that's maybe a little bit surprising, or it conflicts with the previous example of powers of a half. The powers of a half managed to converge because the terms were getting small quite fast. So although you were still walking forward, your step size was decreasing in such a way that there was a limit, namely 1, which you never got beyond. And you converged to that limit. You got closer and closer to that limit. The harmonic series, in some ways, is behaving in a similar way. You're taking steps forward. The step size is decreasing. You step forward 1, then you step forward a half, and a third, and a quarter. So you are taking shorter and shorter steps. However, they're not getting short fast enough. There's still enough weight and there's still enough travel in them so that if an observer waits around long enough, they'll eventually see you pass any particular point, travel any particular distance. So it's a divergent series. And the harmonic series is very special because it marks the borderline between convergent behavior of such sequences and divergent behavior. It's kind of, all the things that get, well, it's to do with series of this form of 1 over m, where we raise m to some power. In a sense, the harmonic series, which we'll understand more about in future lectures, it's kind of like the borderline between convergent and divergent behavior, in some sense. Okay. Sometimes at 1:35, 50 minutes. So, okay, so that's the kind of introduction to it, but I showed you the pictures of the Beetham Tower at the start, you'll remember. So what does this have to do with the Manchester Tower on Deansgate? Okay, so the interesting thing about the Manchester Tower on Deansgate, its whole reason for being, of course, is that it's got this funny shape that it has an overhang. If you go up to the restaurant or the bar there, halfway up, I think there's is there some glass panels in the floor somewhere that you can look down? Is anybody there? Is there glass panels in the floor? Nobody knows? I haven't been there myself. Anyway, this is the aspect of it. So that gives us this general problem of building towers and trying to arrange overhangs in, okay? So an overhang is, so there's a tower of blocks, okay, pretty simply. An overhang, okay, there's no overhang there. An overhang is when the blocks are doing that, okay? When the edge of the top block is overhanging the bottom of the tower, and there's some kind of overhang here. Okay. Now, how much of an overhang can we get? So you can keep trying to make it bigger. Of course, eventually it falls over. With any finite collection of blocks, there's a limit to the overhang you can get. You can get a kind of a biggish one, but if you get too greedy, it falls over. But you can try and build it in a systematic way. I mean, what's the largest length of overhang you can get with 2 blocks? Well, it's going to be a half of whatever the length of the blocks is. It's going to be a half of that, right? So you could position the top block exactly halfway along. Okay. So that gives you an overhang. That gives you an overhang of length a half. Now you can try and put more on top of that, but if you add any extra, they're going to fall over again. So if that's the maximum you can get with 2 blocks, then you see we don't want to knock that bit over, so we can add an extra block, but we have to add it at the bottom. So we keep the top 2 blocks as they were, and we just add an extra block at the bottom, and we increase the overhang. We've got an overhang of a half, and then we've got a bit extra. It's less than a half, but there's certainly a bit extra, a bit of an overhang there. If I push it any further, it'll fall over. So I can't increase the overhang by adding something on top. I want to keep that as an optimum stack. So instead, I'll add one at the bottom. So be careful, I don't want to lose it halfway. Oops. Okay, that's close to optimum for that many bricks. How many bricks? 4 bricks. So you keep repeating this. It becomes a little bit more delicate as you go. There's no glue, there's no trick or anything. It is just blocks. They're balancing on top of each other. Have we reached it yet? Just one more. So how much of an overhang will be developed? I'll just add in one more just to make it. Yeah. How much of an overhang will be developed there? Well, it might be a little bit difficult to see with the perspective, but we've just about reached the point. Just about reached the point where the top block is completely outside of the support. Okay, it doesn't quite look like that because of the. Well, I don't have one more, so. Some of them I haven't done right, I think. Maybe this one. Yeah, I think just there, the top block is outside the support of the bottom. So we've got an overhang of at least one there. At least an overhang of distance one. That already is a little bit paradoxical, I think, that you can have an overhang where the top block is completely outside of the support of the bottom block. Of course, the Beetham Tower is held together with nuts and bolts and stuff. These aren't held together with that. It's just each one is supporting the one above it. Yeah. So this raises the question. I mean, if I'd stolen more of my kids' toys, how high a tower could we build? Okay, we can build a tower of any height. How much of an overhang can we produce? Can I keep going like this? Or is there a limit? Is there, because the increase in the overhang is getting smaller and smaller each time. In fact, this top one could go way out, actually, probably. The increase in the overhang is getting smaller and smaller each time. So is there a limit to the overhang you can produce? Okay. So that's the question we're going to consider now at the end. So this might change your understanding of the world a bit. I know it's a lot to ask for 9 o'clock on a Wednesday morning, but it may happen. Okay, here we go. So here's one I prepared earlier in my office, much less blocks, with the top one overhanging the overhanging the bottom one. So how far can you go? Well, we're going to quickly analyze the problem. Okay. So the overhang is measured from the edge of the top block back to the edge of the bottom supporting block. Okay. The blocks of width W, you can see. So with 2 blocks, you get an overhang of a half W. With 3 blocks, you get an overhang of a little bit more than half of W, and so on. Now, what principle was I using there as I built them? I arranged a stack of blocks. Okay, I had a stack of n blocks, and this had a certain amount of overhang. But the best way of taking your blocks and adding one at the bottom is to position the center of gravity of the top group of blocks so that the center of gravity lies just on the edge of the new supporting block you're putting in at the bottom. If the horizontal location of the center of gravity of the top group of blocks if that center of gravity is supported by the bottom block, then it won't topple over. If the center of gravity of the top group of blocks, if it passes outside the supporting block, then gravity pulls the whole thing sideways and it all falls over. So you get this equivalence that the overhang obtained from stacking n blocks in total, it's equal to the location of the center of gravity of the upper n-1 blocks. So this group of upper n-1 blocks that I'm about to add to this new block at the bottom, its center of gravity is located somewhere about here, horizontally, as measured from position 0 at the right. So that center of gravity, I'm just going to place it so that it lies just on the edge of the bottom block, and then the whole thing will still balance. And I'll have increased the overhang slightly. Okay? Because the center of gravity is just ever so slightly to the left of the bottom block in the upper n-1 blocks. And we can actually identify how Hn develops. H1 is 0. So if you got one block, how much of an overhang can you get? So you measure from the edge of the top block to the edge of the bottom block. Well, the top and the bottom block are the same block. So there's no overhang, there's no distance. So the overhang you get from one block is 0. If we use this idea of the locating the center of gravity, we get this recurrence relation for Hn. So the overhang you get for n blocks, it's the center of gravity of the upper n-2 blocks, and then you're adding a new block. So where is its center of gravity? Well, the center of gravity of the new block is kind of halfway along the block, but there's an averaging process. You only add on this fraction, 1 over n-1 of the location of the center of gravity of the new block that gets added to the existing stack. So we get a recurrence relation. And if we look at how this develops, so H1 is 0, as we said. H2 is W over 2, yeah, because you position the second block halfway along the first one, so you have an overhang of half of W. W is the full width of a block, an overhang of half of W. H3, so you just unravel this recurrence relation. So H3 comes out as W over 2 times 1 plus a half. H4 comes out as W over 2 times 1 plus a half plus a third. Of course, you recognize that. That's the beginning of the harmonic series. In general, Hn is going to be W over 2 times the sum times the n-1th partial sum of the harmonic series. Now, what did our analysis of the harmonic series a few minutes ago just show? It showed it was a divergent series. But if you wait around long enough, you will see partial sums of the harmonic series grow to as big as you want. Okay? Now, I'll skip over these bits, but we then go through an analysis of this, of how big this partial sum is by comparing it with an integral. Of course, we're comparing it with an integral of 1 over x. So you may remember the integral of 1 over x is the logarithm function. So we get to this, I'm skipping over the details because of the time, and not what I want to emphasize, but we get to this final approximation. So this gives an approximate value for the overhang in a stack of n blocks. It's W over 2 times basically the logarithm of n. And there's an adjusting error term 0.6. But it's basically W over 2 times the logarithm of n. And that logarithm function, of course, gets larger and larger as n gets larger and larger. But the logarithm function gets large very slowly. So supposing, so I started off with this little stack here, and I got an overhang of a few centimeters. Let's be a little bit more ambitious. Let's try and get from here, say, if I started building my stack here, maybe to get it all the way over to the door. I've just chosen 3 meters. So could we get an overhang of 3 meters? Well, according to this, we can. We've got enough blocks and we stack them up enough. The overhang is increasing like the harmonic series. So in theory, you just wait around long enough, we should see the overhang here. So the stack begins at the edge of the table, and the topmost block will be positioned above my head here. Now that definitely seems strange and paradoxical, that you can build a self-supporting tower here of little blocks, and the edge of it is going to be way over here. Seems very, very strange. Of course, it couldn't happen in reality because it would have to be pretty high. If you stick in the numbers, so each of these Jenga blocks is 7.5 centimeters wide and 1.5 centimeters tall. So if we want a Jenga stack to have an overhang of 3, so measuring in meters, we want the overhang to be 3. So the width is 0.075 meters. We need to solve this equation for n. To find n is the number of blocks I'd need. Now if you do it, you have to invert the logarithm function, which you do with the exponential function. You get to this approximate solution for n. n is 3.0 times 10 to the 34. So 10 to the 34 is 1 followed by 34 zeros. It's an enormous number. It's probably bigger than, I'm sure it's well bigger than the number of atoms there are in the known universe, or something like that. So we need an awful lot of bricks to build this tower, which only overhangs approximately to here from the edge of the table. How tall would that tower be? Well, each of these is 1.5 centimeters tall. So if there's 3.0 times 10 to the 34 of them, multiplied by the height of one of them, which is 0.015 meters, you get this distance here, 4.6 by 10 to the 32 meters tall. So it's 4 followed by 32 zeros meters tall. That's how high the tower would be to get the overhang over to here. Of course, that's an extremely long distance. By some measure, it's approximately 520,000 times the diameter of the observable universe. So that's how tall the tower would have to be. So have to go way out of our galaxy, the edge of the universe, and then do that trip. Well, that's only the radius of the diameter. So do that trip 1,000,000 times. If you could build it that tall, the top brick would be over here. So that's a demonstration. It gives you a feeling of how the harmonic series is a divergent series, but it's diverging extremely slowly. It's growing extremely slowly. And that idea of how tall the tower would have to be to overhang to here is an illustration of how slowly it's growing. Okay, I'll put all these slides up and everything, and there's a follow-up article which investigates overhanging block stacks in more detail there, which you can access. Okay, I shall see you all next week.